Okay. Uh, okay. So for today's class, I would like to start with reviewing chapter 2. Maybe um, two problems. So this is the first one. Yeah, it's related to stress-strain problem. With the ultimate questions within this problem is to asking the Poisson ratio, which is the ratio between the strain on the transversal axis and longitudinal axis. So you can try first, okay, to check check the answers. I'm not sure whether I put this in the exercise or not. I think if not, maybe the one that is similar to the exercise. So as a reminder, next Tuesday we are going to have a new chapter 4, and the next Tuesday, April 18th, that will be our midterm exam. Okay? And midterm will be based on chapter 1, 2, 3. So statics, the stress strain problems, include the some of the mechanical property, some of the safety factor, and all sort of those related stress strain problem, chapter 2, and chapter 3, which is the axial deformations. And for more exercise on chapter 2, please refer to the attached file in the Moodle. I attached the exercise and mentioned several problems that you might need to study. I also mentioned, I think, one link that has, I think, good playlist for statics review. There is one YouTube channel that I think it has a good content, because the creator is also a professor in mechanical engineering in the United States. So I think that will be very good content, and how he explained is seems more practical and with a reasonable approach. Even if you are maybe not familiar with the subject itself, if you listen to the course by that professor, I think he can deliver good explanations. So there is a cylinder in our case here, a brass cylinder, and it is compressed, okay, between two plates, rigid plates. Okay, so if you see the picture, that is how we compress with a force, axial force P, 20 kilonewton. Okay, so if we are going to compress this cylinder, which means that that there will be a shortening, and it's mentioned in the first question. if the measured shortening of the cylinder due to this compressive force is 0.0283 millimeter, what is the modulus of elasticity for the specimen? Okay, so to give you more context on how we could observe the problem, let me draw the diagram for the specimen. So let's say this is the plate. So this is after shortening. So let me describe. This is before shortening. So there is a change in the volume, right? I mean, not the volume, the shape. Okay, the volume is still the same, but the shape is getting, so the cylinder getting shorter, the height, right, getting shorter, and the width is getting larger. Right? So that's why it's asking the Poisson ratio, because there is a change between the height and the width, right? The transversal axis and the longitudinal axis. So let me rename. This is the new length. Let me write the new length as L with star with asterisk. Okay. And the original length with L, or L0, L origin. Okay. And then you have a force, axial force, that compress this cylinder, both sides. Okay. Oh, the width. Let's say the diameter, right? The width is the diameter. Let me write diameter. Diameter is, this is the D. Let's say this is D. The origin, diameter, origin. And this is after compression. So let me write D with star, asterisk. Okay, now the first question is asking E. Okay, what is E? Modulus of elastic is equal the stress divided by the strain. Okay. Now to get the stress, we get from, so stress we get from the F or P over A, right? But of course, if we are talking about the stress here, and if you want to compute the area, which area you are going to compute? After or before? After or before? after record. Yeah. Which diameter we are going to put into 8?
In the before.
Yeah, the before. Yeah, before. Because that is our estimated computations, right? If we are compete with this one, it means that this is for the next one that is going to happen, right? Okay, that's logic. Okay, now we take this as let me write with the negative because it's going to be compressive. Negative signs, and then this is pi. This is d0/2 squared, or -4 pi up p pi d0 squared. Okay. So this will be -4 multiply with 20 kilonewton and this will be 15 millimeter squared. Okay, let's check. Is going to be I'll multiply with 1,000, 113.176 megapascal, or this is actually the Newton over millimeter squared. Okay, that's the stress. And then the strain is the delta L divided by the original length. Okay. The delta L, so the final length minus the original length divide the original length. So what is the shortening? Oh, it's already delta L, so we don't need to calculate that. Okay, so we can directly write 0.0283 with minus because it's shortening, divided by, what is the L is 25. So this will be 0.0283. So negative 1.132. Okay, that's the strain. Then we get the modulus of elasticity. Which is divided with this. Okay. So it's 99,000 MPa or 99.978 GPa. Okay. Well, because I think it can be rounded to be, I think 100. Okay, I think still okay. Okay. In any case, if you are in the exam and you want to simplify it, it becomes 100 like that, it's possible. I think this is still okay. Because in terms of mechanics, the rounded decimals is not really significant. Okay. So we can round it into, like, if you get 99.9, you can just write 100, still okay. So that's the first question. The second question, if the increase in diameter due to the load P is 5.8 with 10 by power of 3 millimeter, what is the value of Poisson ratio? Okay. I think should be -3, right? Do you think so? Should be 0.0058. Right? I think in terms of scale, right? I think that's more makes sense. Okay. So the question is, this is not 3, it's supposed to be -3. Okay, now the second question, if the increase in diameter, which means that this D, okay, this final D. So the increase, which means the delta D, so we are going to have another strain. Okay, so I think it's perhaps better to take the to denote the strain here as, I think, Y, okay, and the other strain is X. Okay, I think it's better to differentiate the two strains. Okay, so this is A. Okay, so B, the strain in X, okay, which means the delta D, or maybe let me write D minus D0 divided by D0, or delta D divided by D0, and the delta D is it's increasing 0.0058 millimeter divided by diameter is 15. .8667. That's the strain. And then the question is asking the Poisson ratio. The Poisson ratio is negative strain of transversal divided strain on longitudinal, or in our case, the transversal, that is on the X, is negative E X divided by strain Y. So this is divided by it's supposed to be 0.3415, okay, the Poisson ratio. So the answer is this, 100 GPa and this. Okay. Okay, to remind you, the midterm will be 18. Next week we move to chapter 4. But the Friday class, I think I'm still doing one more tutorial, chapter 2 and 3 probably, to prepare your midterm. And my suggestion is, if you need more review, perhaps the statics and I think the chapter 2, lecture. If you need more, then watch the my link on the Moodle. There is one playlist. The creator is Jeff Hansen. He is also writing the books for mechanics and statics, and I think his explanation is very good. Has a good approach, and if you want to review, you can watch his video. But his video is really I think he has 70 to 80 videos for the playlist, so you could skip for some parts and maybe focus on the practical problems. I think he has some exam 1 review, exam 2 review. You watch that. I think that's very helpful. And if you want to watch more, he also has the playlist for the mechanics. I haven't put the link, but you can check from the same channel. And sometimes I took some part of his method in the lecture also. So you can watch that for review, and I hope it's helpful. Because the key for the course to get to understanding the problem solving is through the discussion and all the process. So if you want to know more, then you need to try to do it by yourself. Okay? Try to focus. And do not rely too much on, maybe if you look for solutions in the internet, sometimes it's not very clear. So you need to focus first, watch the necessary materials, review, and that is why I'm suggesting some YouTube channels. I think there are other YouTube channels that explain the course as well. That is, I think, very good, but I'm not sure it will be fit with our course. But I think the one that I mentioned, it's very, I think, very suitable for our course. Okay, now next question. The second one here. Okay, I think this is I give this in the attachment. I think I forgot. I think I give, right, or similar to this. If not, then similar. I remember the picture the same, but I forgot the same number or not. Okay, so Boom AC supported by bar BD. So BD is here. Okay, has support. Assume pin at B is adequate or sufficient to sustain the loading, and that the design critical components are the bar BD and the pin at C. Okay, so which means the critical means that if we change the design on BD or the pin C, then it will significantly affect the whole system, which means also that we are going to see some safety factor issue, and it's mentioned here. The safety factor against failure of BD by yielding is, we have safety factor 3.5, and safety factor on the shear is 3.3. Okay. Determine the required thickness. Okay, the T. It's also mentioned here. Okay. Thickness on the BD, and then it has also width B, and then determine the required diameter at pin C, and this is all other information that needed. Okay, so perhaps every time, maybe this is my suggestion and tips. Every time you see the question and this is like a very long words, what we need to do is we need to maybe underline the important words first, the keywords. So the important words here is we have the safety factor here. Okay. So you can do either maybe drawing the free body diagram first, or writing all the necessary formula needed. Okay. That's two things that you can do first. Okay. So I think because we have safety factor here, so to help me to relate the questions, then perhaps we can take the safety factor as, if you remember, sigma allowable, sigma yield, over the factor of safety. Okay. Or the tau allowable, the shear. This is the yield for tau over the factor safety for the for tau, and this is for sigma. Okay. Okay. Okay, and then perhaps we start to take the free body diagram. Okay, remember, the question is starting, the statement, the first statement is the boom AC is supported, which means that the main frame or the main body is this one. Okay? Because it was the one that's supported by this. So we can treat the BD as this as force. We just force has a BD. Okay, so this is AC, and then BD is on the middle of AC, right there. So let me go in there, FBD, and then we have P on the side, and A, this is P. Okay, now on C, remember, on C, we have pin. Whenever you see the pin like this, it has like a circular, it means that it can rotate, right? So the reaction force here is only X and Y, without couple, because it can rotate, right? So, and it doesn't matter if you write the direction is maybe wrong direction, still okay, because you will get to know whether it's correct or not after calculations. So let me just write this going there. So Cx. And then L is 1.8. So L is 1.8. So L 1.8. So this will be 0.9. So 0.9 here. And also 0.9 also here. Okay. And then so if we take, for example, we have a triangle here, right? And it doesn't mention any angle. So we need to find the relation first. Can we find relations to make this BD comes this directions? Because every time you have the free body diagram, the one thing that you need to do is you need to find the equilibrium, right? And one of equilibrium that needs to be find first is the sigma moment. So you need to find sigma moment equals 0. To find the sigma moment, all the diagonal force, you need to make it straight up, right? And you need to know the relation with the angle or the trigonometric relation. Usually, something like this happen. It's supposed to have 3, 4, 5 triangles directly sides. Okay? So we need to make sure, confirm. Okay? Is it 3, 4, 5 or not? So we have H is 1.2. The L over 2 is 0.9. And I think this is 3.5, right? So we can take this 3, 4, 5. So we can write in our free body diagram, this is 3, 4, 5. So the cosine here is 4 over 5. Okay, 4 over 5. And what is cosine? Sine. Okay, so we take the moment, and since we know P, so I think the best way to make this as our perspective. So we need to take the moment at C. Okay. So let's say we're going to take that direction is positive. Let me write that's 4 over 5 FPD. So negative P 1.8 plus 4 over 5 FBD 0.9. This is equal to 0. P is 11 kilonewton. So 4 over 5, or maybe let me write FBD is, this is 11 kilonewton. Okay, so this will be 27.5 kilonewton. Okay, now sigma Now we can say the FBD as a force that is required for our sigma. So we can take the FBD over A, right? Now the cross sections between the BD is the BT, right? So this is FBD and then BT. Okay. Now remember that we have the safety factor. Okay? We have the safety factor. So the sigma, this is sigma allowable. So we need to write the sigma allowable as sigma yield divided by the factor safety of this sigma is equal FBD divided by BT, right? And then from here we get T is FBD divided B, and then multiply with factor safety for sigma divided by sigma yield, right? Okay. So I start from here, start from this, the known that we have FBD, right? This F is going to make into stress with this area on the rectangle of BD, because BD has the width and the thickness BT, so this will be the area, the cross section. Okay. So this will be its sigma, right? And because the sigma, it needs to have some safety factor issue, right? So it needs to have the sigma needs to have the sigma yield over a factor of safety, because that is the sigma that is allowable on the FBD. So we have this, and we need to find the thickness, right? And then we can rewrite it to this equations. So that will be so safety factor is what, 3.5? So 27.5, 3.5, and then B is 25 millimeter. Oh, this is kilonewton, sorry. Kilonewton and 3.5. And the sigma yield is 250 megapascal. So this is 15.4 millimeter. Okay, that's the required thickness for BD. Okay. The next question is determine the required diameter of the pin at C. Okay, so what we need to find at C. Remember the C is actually, it has, remember that we have here, right? This is the C. And it also gives us this view, okay? So every time you see in any field something like this, you're supposed to relate it to the shear. Okay? It's either single or double. And how about this? It's double, right? Double shear. This has both sides. Okay, so we need to find V, the shear force. And how to find the shear force? We need to find the reaction force at C. What is the magnitude? Okay, so we need to find Cx and Cy. Okay, so we right here. So the sigma for the force, we can start with directly both this. So from the picture, we get that we can take the sigma moment. Okay, we can take the sigma moment at B. Okay, we can take the sigma moment at B to get the Cy. Okay, so because it has the same distance, we can make sure that Cy is equal to B, right? Okay, get it? From the sigma moment B here. So if we take this, because the length is the same, right? So L over 2 P minus Cy L over 2 equals 0. So P is equal Cy. Oh, this is plus. So negative, sorry, negative. So this is negative 11 kilonewton. Okay. And then Cx from the sigma on x-axis, the Cx is equal negative 3 over 5 FPD, right? Okay, so this is negative 3 over 5 multiplied with 27.5. This is 16.5 kilonewton. So we got Cy, we got Cx. So C is the magnitude of the two vectors Cx squared plus Cy squared and its square root. So this is 19.83 kilonewton, and this will be the shear force. Okay, this is going to be the shear force. And then remember, the tau, we need to take into the safety factor first. So tau yield divided by factor of safety of tau of the shear. So this will be what, 410 MPa divided by 3.3. Okay, and this tau is supposed to get the V over 2A, right? The V is from the 19.83 kilonewton divided by 2A, the area, 2 pi D, right? This is D divided by 2 squared. So D is the one that we want to know, right? This is equal to the sigma, the tau allowable, 410 MPa divided 3.3. So you need to find D. I hope you can solve this. Okay, just compute and you probably will find D. Right? Okay, I think that's it for today's class. So see you next Tuesday. Tuesday we move to the new chapter. Next Friday I will give you more tutorials like this. Okay, I suppose that it can help. And yeah, I think that's it for today. So see you next week.